Welcome back. For this section, we have been talking about various correlation functions. We looked at the time correlation. So, I want to remind you something that we had looked at earlier, because in this context of time correlation as well as space time correlation function, we had looked at vibrational spectra. So, vibrational spectra comes from velocity autocorrelation function. As you see on your slide, VSCF provides necessary information on atomic motion with respect to time. Fourier transform of VSCF provides power spectra of atom, which is generalized vibrational spectra. What we mean by generalized vibrational spectra is that density of states is weighted by the square of the vibrational amplitude, and that is where I wanted to show that while for the g of r, which is radial distribution function, you took Fourier transform that goes to static structure factor. And if you take the Fourier transform of GRT, which is density correlation function, then it goes into dynamic structure factor, which is connected with the neutron diffraction and inelastic scattering. That is where now we go into vibrational spectra. So, now it kind of connecting the all the different quantities, because atomic structure is also presented by the molecular spectroscopy, which is Raman spectroscopy. The Raman name comes from a scientist from India, Chandrasekhar Venkata Raman, who got Nobel Prize in 1930s, I believe, for the invention of this whole idea that if when you hit a particular light wave onto a molecular system, there is a scattering of the light, and that scattering of the light, the frequency of the scattered light is shifted from the original incident frequency, and those Raman shift, which is why it is called Raman effect. The Raman shift are what is called vibrational frequencies, which are associated with the specific material, and that is why vibrational spectroscopy or Raman spectroscopy in particular, which is in the visible region. So, you can use the laser, the visible light, and shining that light you can find the scattered light frequency. That is very interesting effect, which was invented by Raman. And so, the Raman spectra gives you vibrational spectroscopy, and those peaks, which are the scattered frequency peaks, are essentially specific to material. So, if you have an unknown compound and you shine a laser and you look at the Raman peaks, they provide you information about the compound, and that is used quite a bit nowadays in forensics and all of those other areas. And so, if you look at, we can also calculate vibrational spectra, which has 1-to-1 correspondence with the Raman spectra. So, it may not be exactly Raman frequencies, but you can see all 4 frequencies as we move forward using velocity autocorrelation function, which is what we take in the time domain, which is autocorrelation function with respect to time. So, C t a as 0 and property a at time t. So, if you look at the t tends to infinity on your slide 1 over tau, then you have this velocity autocorrelation function for an arbitrary property. But if you look at the Fourier transform of that property, in this case velocity autocorrelation, that is where phi omega, which is the frequency domain. So, we go from time domain to frequency domain, C t cos omega t dt. This is a Fourier transform, just what we saw in G r going to static structure, VSCF velocity autocorrelation function going to generalized vibrational spectra. And that is where we saw the again the cubic ice and its spectra with using simple point charge potential that I calculated, and that is where we were able to get all 4 regions of the vibrational spectra, which were observed by the Raman spectroscopy. So, I did bunch of Raman spectroscopic experiments on the water and ice molecules, and what we were able to see is the lattice vibration from 0 to 250. Then we had torsional and vibration, which is essentially rotational. Then you have bending vibration about 15 or 1600, and then we have stretching vibration, which is typically 3100 to 3300 wave numbers, and wave number is essentially reciprocal of the wavelength. So, that is where it is called wave numbers. So, with these wave numbers frequencies, we can observe high frequency, low, medium frequency, torsional, and the lower frequency, which is called lattice vibrations. So, with that understanding, we saw that again using molecular dynamics and correlation function theory, we are able to now take it to from let us say 210 degrees Kelvin, and we are going to 240 degrees Kelvin, and now you see that atomic motion is happening there. This is the dynamic property, which is the vibrational property. So, the vibrational peaks have become much broader, especially in the low frequency zone, where it was a sharp peak at close to 180, 120 wave numbers. Now, this if you look at the as we heat the ice, cubic ice, then the vibrations of the atom, especially the rotation and bending, kind of become mixed up. So, that is where if you look at, there is no bending peak here, but there is a whole bunch of peaks here, but there is a sharpening of the stretching peak. So, now you can see two stretching peak, OH stretching 1, OH 1 and OH 2, each one represented by frequency V 1 and V 3. So, the frequency is 3100 wave numbers in the experiment, but here is moved out with a slightly higher numbers. So, you can see there is a correspondence between these frequencies. So, further if you heat it up close to and above the melting temperature, you see that the crystal structure is completely gone. So, there is no lattice frequency, there is no lattice remaining. You can see now there is some rotational frequency, and now you also see emergence of the bending, because now these are water molecules, and so these molecules are able to rotate, able to bend, able to, but there is no lattice now. So, there is no lattice frequency of the cooperative movement, but now there is a lot of stretching, and that stretching is two stretching, one is OH 1 and OH 2. So, all these spectra are observed by the Raman spectroscopy. So, now you can see this table where we looked at different peaks and their positions, and if you look at, and then we compared that with the real experimental, and we found that the trend was extremely similar to the experimental vibrational Raman spectra. So, we looked at 70 degrees Kelvin, 140, 210, 240 and 280, and we looked at the first peak, which is what you are looking at, the what we call lattice peaks, when there was a crystal structure of ice, but it goes away at 280. Second peak is bending, or what we call the rotational peak is consistent, but you can see at 240 there is essentially broadening of the peak. And the third one, which is the bending peak, there is a quite good trend that we are watching, that the bending peak is starting with a higher value and going slightly lower values. But then if you look at the temperature dependent variations from 3346 moving to 3422, and the fifth peak, which is OH 2, 3462 wave numbers to 3632 wave numbers, we see this similar trend in the Raman spectroscopy, where V1 frequency or OH 1 frequency stretching increases with the temperature, and also the OH 2 increases with the temperature, as you can consider that as the temperature is growing, more vibrations are happening. So, for that OH stretching, it is very physically connected to it, and I think that is the very important factor that I wanted to bring back to this whole discussion of velocity autocorrelation function, or what we call time correlation function, and the linear response theory and Green-Kubo formulation that we are looking at this particular juncture. Now, we are going to move into stress and deformation in solids and their atomistic approach that allows us to create stress and strain. So, I will begin with some simple formulations first, and then we will go into understanding of stress and strain. Thank you.